astrophysics. And so that is where I started into supercomputing. I then started working in multiple supercomputing centers, the Arctic Region Supercomputing Center, the San Diego Supercomputer Center, and then I created the Texas Advanced Computing Center, ran it for 12 years. I've been with DELL as a contractor and as a full-time staff for the last several years. I do HPC mostly, but I'm doing some AI strategy for DELL Technologies as well. Let me turn it over to the other two instructors.
Sure. John Lockman here. Also longtime HPC guy, computer scientist by training. Roughly 20 years ago was when I started to dig into the beginnings of AI, although we didn't call it that then. Worked with Luke on a lot of projects over the years, and now we're here in the AI Innovation Lab and building lots of different types of systems to handle different workloads and trying to really get a handle on all of the different new hardware technologies that we can take advantage of for, for handling AI workloads. Along with that, not just the hardware, but also the software side of trying to help modernize our simulation and modeling workloads, bring things into a containerized space so that we can really expand our horizons on how we think about computing.
I'm Luke Wilson. I'm an HPC and AI Distinguished Engineer in Dell's HPC and AI Innovation Lab. I've been with Dell for 3 years, helping to push the state of the art in AI and high performance computing in the intersection of those two spaces. Before Dell, I spent 12 years at the Texas Advanced Computing Center as a member of HPC research staff. PhD is in computer science with a focus on using artificial intelligence to improve large-scale computation.
Sorry, slides are advancing on their own here with me. Go ahead.
That's it?
Sorry. So we normally do class introductions because we normally teach this in person. And so let's see, how many do we have online? 38? That might be difficult with the time that we've lost to do those. So we'll probably encourage you to introduce in the chat window. John, Luke, and I have already done that, but we encourage you to introduce and say whatever you want to say about yourself in the chat window. We assume with this class that everybody has probably programmed before, but there might be folks in it that haven't, and that's fine. Curious if you've programmed in with Python, and if you've done any classical machine learning techniques, and if you've done any deep learning techniques. So you might want to share that in the chat window, and that will give us an idea as we present how to adjust scope based on what we see in that chat window. So I'm giving this introduction, and the first thing I want to say is it's an awesome time to be interested in artificial intelligence. There's so much buzz around it right now, and this all really started several years ago. Actually, it's about 10 years ago when Hinton's team at University of Toronto had some amazing results in image classification in a significant competition, and showed that they were able to train image classification models to be incredibly accurate. And it was the beginning of people realizing that we finally had enough compute power now, and enough, as well as enough data, to do some amazing things and to make these techniques that have been in existence for a long time, actually, practically useful. And so we are seeing an explosion in interest and even usage and real impact of AI. It's one of those few technologies where you see statements this grand. Now, people are prone to hyperbole, especially in the press, but we see real technology leaders and visionaries making incredibly grand statements like AI is the most far-reaching technological advancement in our lifetime. It changes every industry, every company, everything. That is an incredibly grand statement, but it is also probably true over the next decade. For some companies, it's already happening. Most companies will want to think about how much of their processes they can transform into digital processes, and then use higher level data analytics and even AI to augment their ability to execute. And it might be creating some autonomous systems, it might be augmenting human intelligence, but AI is going to play a role in this, especially in this era of a subset of AI called machine learning. and a subset of that called deep learning. So, people often ask me to give talks on trends. I'm happy to give talks on trends, but I really like this one slide in talking about the certainties that are driving AI, because you can be wrong about trends, but there are a couple of certainties. One is that people will always need hindsight because we learn from experiences, but they will always want insight and foresight. Now, we take that for granted, but we spend a lot of our day thinking about what will happen next and how I can influence what will happen next. You can't run a good company only looking at past data. You have to plan. We make plans, we make projections. This is built into our DNA. We needed to know whether the tribe across the river valley was going to attack. We needed to know how to avoid the saber-toothed tigers. We needed to know if this bad weather was going to be dangerous to our family and our tribe. So we've always wanted to learn from the past and present in order to understand the present and future and even impact it. So that is a certainty. The only other and I should say that certainty has led us to creating increasingly powerful methods of data analytics. So descriptive analytics is a hindsight method, right? What happened? Can I pull a database report and see how many pairs of red shoes I sold over the last 4 quarters? And is that number declining? That maybe indicates that red is a color that's falling out of favor. So hindsight, data analytics techniques that improve our hindsight, improve our human ability to have insight and foresight. But we have continued to develop our data analytics capabilities in order to not only describe the past, but to analyze the present and predict the future, and even to play what if scenarios about the future. And so as we move up this axis, we are increasing our ability of analytics to not only talk about the past, but to help us understand the present and future. It doesn't mean we're relying on it totally, but it is greatly augmenting our intelligence for understanding the present and future. And the one other certainty is that data scale will continue to increase exponentially. This should not be taken for granted because not everything increases exponentially. The number of smartphones in the world increased exponentially for a while, but then it followed the standard S curve because most people don't need more than one smartphone. And right now, a few billion people in the world have one. So not all 7.8 billion have one, but we've already seen that curve asymptote in the traditional S curve shape. So some curves that start exponentially taper because they're governed by some other upper limit. But so far, our ability to produce devices that create data and to increase the performance of those devices yields a double factor that appears that it will increase the amount of data production, the rate of data production exponentially for a long, long time. And it's not hard to see that both those exponentials are at play here, even if you believe there's nothing beyond the current semiconductor technology and Moore's law peters out. There's still the other variable of the number of devices that we produce. We have not yet begun to instrument the world. We have some satellites, we have some ground stations, but the vast majority of our environments remain uninstrumented, while the cost for instrumenting them is decreasing. And so they will be instrumented. As our population rises, we become more dependent on our infrastructure. We need resiliency, we need security. We will instrument more and more of the world. There'll be more and more devices, and that will contribute to this global data glut. And that leads us to this growth in data analytics technologies. I showed it in one forum 2 slides ago. I borrowed this slide from Intel because they list some of the technologies on the right that correspond to the historical and current methods of data analytics on that curve on the left. So viewed in this light, the current AI buzz is not a revolution, it's a natural evolution of our ability, of our desire to want to understand more and influence more things, and the improvement in our analytics abilities and the data on which to apply those abilities. So viewed in this light, AI was inevitable. It is absolutely a different way of thinking. In particular, the machine learning and deep learning models are very different than other explicit methods. So it's fair to call it revolutionary. It's fair to call it transformational. But it is also equally fair to say that it was an inevitable evolution of our desire to constantly understand what is happening, what will happen, and how we can influence it, and thus collect more data and improve our data analytics techniques in order to improve our human ability to do so. And so we're in this era of diagnostic, predictive, and prescriptive analytics now, facilitated by machine and deep learning and several other technologies. We are not yet in this era of cognitive analytics. It's fun how many AI companies put the word cognitive in their name or in the descriptions of what they do. That seems a little bold to me, but you know, marketing is marketing, and it is what it is. So most computer scientists would probably not say we've built truly cognitive systems yet. And there's great arguments over whether artificial intelligence is even an apt term for what we're doing now. But the point is, we are definitely in the era of predictive and prescriptive analytics, and certainly research in the early days of cognitive analytics. So I gave you those two certainties. So what are the trends that are governing this? One is that AI expectations and impact are driving massive new software investments, services, companies, and silicon investments. It's the most exciting time in silicon since at least 30 years ago, as everybody wants to cash in on this AI boom. And they're realizing that the general purpose CPUs that can execute the algorithms are not optimized for them. So NVIDIA, which has done a tremendous job in computer graphics over the years, was in the right place at the right time. And the way we currently express these deep learning algorithms lends itself well to GPUs. Doesn't mean GPUs were designed for deep learning, although now there are architectural features in NVIDIA's GPUs that are designed for deep learning. But the ability to do this dense linear algebra well was particularly useful for solving some of the kinds of equations that Luke is going to show you later in the day. So software, services, and silicon booming in all three of those. I need to update this 3,000 in the NVIDIA ecosystem. It's now several thousand in that ecosystem. You're seeing lots of services companies and lots of startups doing silicon. I mean, it's actually a cheaper time to spin up your own silicon chip than it's ever been. It's in the low tens of millions of dollars, and you can get someone else to fab it now. So it's an interesting time to see if you can design something that's better optimized for AI. Maybe it's not perfect for, you know, running Microsoft Office. You're not trying to compete with Intel and AMD in that regard. But for AI training and especially inferencing, there are many companies developing silicon optimized for that. Another trend that is continuing, I didn't put it as an everlong certainty as I did 2 slides ago. These are trends, is cloud continues to increase in importance as a model, but we're starting to see a lot more interest in hybrid cloud growth due to where data is produced and secured. Really, hybrid cloud is not a great term, because we tend to mean hybrid cloud as hybrid on-prem and cloud, and then we leave the words on-prem out of that because that's just the assumption part. The computing is on-prem. So now we call it hybrid cloud because we've also accepted cloud as a mainstay, and it's here to stay. Hybrid cloud refers to combining your on-prem and cloud models, but it is also being used to refer to combining with edge computing as well. There's the reality is data happens where it happens, and that's everywhere in the world. And so we expect a proliferation of sensors and edge computing devices attached to those sensors as we further instrument the world. And it's really about making decisions where decisions need to be applied. So in the current models of on-prem and cloud computing, we tend to make the decisions, we compute the decisions in our on-prem data center or our cloud data center, and then we transfer that decision to where that decision needs to be applied. But in the future, we see many more things, including autonomous things like autonomous vehicles, in which the car is where the decision is applied, not the cloud. And therefore, especially in something that needs to be fully autonomous, like a vehicle, you don't want the cloud being the decision point. You want the car being able to make its own decisions, i.e. be autonomous, in case it loses network connectivity. And because some decisions, every nanosecond matters, like in a crash situation, you don't want to have to relay your video feeds and LiDAR feeds up to a cloud and have the cloud compute, oh yeah, you're going to hit that wall at this speed and with the roads being this slick, and then transfer that decision down to apply the brakes, or even worse, apply the airbag, right? You want those decisions to be made with the maximum performance and lowest latency. And so those decisions are made at edges. So in this future world, we're going to see edge, on-prem, and cloud all tied together. It'll be a matter of economics where many of the decisions will be made, but it will be an issue of practicality as to where the large training will occur, and it will be a matter of necessity as to where decisions are made and inferences are made in many cases. And so this means that smart IoT is becoming real. The term IoT is, I've noticed, falling out of favor. It's too grand a term, the Internet of Things. You know, there's tens of billions of devices in the world that are connected, but they're not all connected to each other. And sometimes they're all, some of them are connected to one other thing. But it is the case that we have more and more devices that are connected, more connected sensors, more edge computing processing and such. We expect this to grow exponentially as we desire to have more and more control over our physical environments, more ability to measure their sustainability, their safety, their resiliency. This means instrumenting more and more things, and this will drive the growth of edge computing, which will be connected to on-prem and cloud computing in this spectrum of computing, in which there are going to be some very interesting data flows and workflows. But where do you apply the intelligence? Sometimes it's going to be dictated by the size of the data and the size of the model you have to train. Sometimes it'll be dictated to where the decision has to be made. And I mentioned this, but there's tens of billions of connected devices in the world. And this is going to greatly change the way, or the balance, I should say, of cloud, on-prem, and edge. The number of cloud data centers isn't going to grow as fast as the number of edge devices is going to grow. The capability in those cloud data centers and on-prem data centers does continue to grow, driven by Moore's law and building bigger systems. But the sheer number of edge devices is continuing at an exponential growth rate, and we expect that to continue. So these factors are creating this big AI market, and the major point of this slide is we're only here. We're at the beginning of 2021. We do see exponential growth for a long time in the AI market. There are reasons this growth is not even faster. We have all heard that there are data silos that need to be overcome for machine learning and deep learning. And that's a true statement. It's unfortunate that it's always phrased as a negative, because if you go back a few slides and remember when our only tools were databases, you wanted your databases siloed. You did not want to have to do the extra work of creating massive ontologies and schemas and tables for data, for different types of data that you didn't fuse together for anything anyway. So it made sense to have a sales database and a support database and a marketing database and a shipping database. And you don't need your marketing people seeing your shipping database and vice versa. And you didn't need to make databases, therefore, that incorporated all of the features that all of them needed. Otherwise you'd have made these huge monolithic databases. So it made, the positive spin on silo was specialized. We had specialized databases in those days. Now, of course, with these higher level analytics techniques, and I've talked about the evolution of analytics, now we have techniques that actually can find patterns and features in these seemingly disparate data types that are all actually related potentially for certain features that we wouldn't be able to find if we couldn't combine the data into a large deep learning model. And DELL often presents an example of when we improved our own means of doing preventive maintenance on hard drive failures. The old method would have been, if hard drives fail, do a database search to see if they're from the same lot, or if they've been shipped to the same locations using the same, perhaps, rough shipping techniques, or if they're happening to the same kinds of customers. And that would be the hindcasting technique. And that might find certain gross features that are common to failures. but it wouldn't find more subtle features that might be a combination of the characteristics of the drive, the way it was shipped, the firmware version, the operating conditions in the data center in which it's being used, and the usage conditions, the amount of reads and writes under which it's being used. And it turns out there might be subtle connections between all of those things that a human's not going to find from reading 5 database reports, but a deep learning technique by fusing all of that data may find. And in fact, we did find some cases like that. And finally, I'll just say you've probably heard of training and inferencing, and we're going to talk about both. Training gets a lot of the attention. It's kind of the sexier thing because in high performance computing, it's the high performance part of AI. But inferencing is really where the decisions get applied. And inferencing devices can be as cheap as the $30 camera that I have over here on the edge of my condo that can do tracking of people moving around in the room. Now that model was trained on a high-end system somewhere, but the model is now applied at the camera that does some basic tracking. And we'll talk more about training and inferencing coming up. We're going to use the term AI sometimes loosely, but today we're really talking about machine learning and deep learning as subsets of AI. This is important to note because there are other techniques of AI. Probably many of you on this call remember the term expert systems that was in vogue. What was that? More the 1980s, I guess, is when expert systems was probably in its heyday. And expert systems were one of the ways we tried to simulate intelligence by having these essentially tremendously nested if then else statements and case statements and switch statements, as we would call them now and such. But basically explicit programming, but trying to account for so many possible inputs that we could make an appropriate decision for many of them. And sure, there were some conditions for if it was none of the above, what you do. It was often ask the user for a different input if it was a interactive program. And so there are other methods of artificial intelligence. Many people are using AI techniques based on graph analytics now, not nearly as many as machine learning and deep learning. That area's not grown quite like those have recently, but it's an area that we think may also explode over the next several years. What's really getting a lot of the attention is machine learning. And that's an application where systems use data to learn. And so you train these models and then you can inference against those trained models, and you can retrain the models as more data comes in. And if you find your model's not quite accurate enough, you collect more and more data and retrain it. And you can sort of think of it loosely analogously as to human learning. We learn from experiences, and then we develop some mental models that when metal things are glowing red, they're probably too hot to touch, right? Then deep learning is a form of machine learning in which we use artificial neural networks. And Luke's going to talk about that later today. And that goes beyond some of the classical machine learning techniques and is really good with unstructured data, the kind of thing that we wouldn't have known how to make an expert system classify, like a bunch of images that might have different cats or different dogs or sandwiches in them. That's not possible easily via explicit programming to look at images like that and determine what it is. But using deep neural networks, you can train models that determine the common features if you have enough data of each type, and become very accurate at classifying new images that have one of those objects in it. Now, Luke alerted me to this diagram, which is actually an older diagram, but it's the, sorry about the slide progression there. It's really, as he says, the slide that we should be using. The other one is nice and simple, and it makes machine learning a subset of AI and deep learning a subset of machine learning. But there are all these other fields in data methods that have some overlap. There are methods of pattern recognition that are machine learning, but there are some that are not machine learning as well. There's overlap in things like statistics and data mining and databases. So all these fields have been around for a long time. And really, probably what you want to think about it all is data analytics at some level. You're using data to get information and knowledge out of it, often that can be actionable and make decisions. And so you could subset these things or use these Venn diagrams within that overall orange box here. But what we care about is what it enables. And it enables things like predictive customer support and fraud detection and chat bots and robotic process automation, and many other things. And so this is what we really care about. We are using data and some methods of data to achieve these outcomes that might be impossible for a human to calculate and figure out, or might just be difficult, or might be slow for a human, or might be expensive for the human you'd have to pay, or might be error prone for the human. So there are many, many reasons that you might use data analytics techniques, often related to performance and cost and increasingly accuracy. So am I covering this? I'm covering this part, Luke or John, I think I'm covering this part and then you're going to come in.
That's right.
Okay, making sure. So machine learning and deep learning help with unstructured data. And so if you go back again to that chart that I showed of data analytics techniques and the evolution of techniques from databases to deep learning, you'll remember that those database techniques are really good for structured data. There's database tables and text data and historical statistics. This is all the kind of stuff we're used to using databases and spreadsheets and things like that. And that's really a huge amount of data that we've dealt with in the past. But the reality is we see images with our eyes. And so we build sensors that take pictures and collect video and collect audio. So these are data to which a regular schema cannot be applied. And so it was inevitable that we would develop more advanced data analytics techniques, because ultimately we want to be able to understand the data that is in the world around us. Not just that we know how to enter into a database, but anything that we could measure with a video camera around the world, about the world around us. And so machine learning, in its simplest, is this method of transforming inputs to outputs. It's a system which maps these inputs, these environmental percepts, to outputs, which are actions or decisions. And the system can be generalized as a function. The function is partial, the function space is unknown. The function space may be discontinuous, but it's really about transforming a set of inputs, say a set of images, to a set of outputs, which might be decisions about whether the image contains a cat, a dog, a sandwich, or any of those other things that you're cursed with having to deal with on an increasing number of websites that ask you to check boxes that have a street light in them, or a bicycle in them, or a mountain in them. And you probably can now guess what you're voluntarily doing and contributing to as you perform that operation of human classification and labeling that data. And so machine learning is in widespread use, and it's really kind of a two general step process, and it can get increasingly more complicated, but you can really think of it as a two-phase process. The left side is the training phase, and you might think of it as the learning phase, and the right side is the use phase or the inference phase. So on the left side, you're taking some machine learning algorithm that you've coded, and you're training it on data. And in the simplest form, it's labeled data. So known data, you train it until to recognize this image has a cat, this image, or in a more deep learning example, this image has a cat, this one has a dog, this one has a sandwich. But it can be any kind of data, especially labeled data is quite useful, that you can train it on so that you can then test it against additional data to see how well it's doing. So when you have a bunch of known data, you carve out a subset of that and train it, and then you test it on other data within that corpus of known data to see how well you've trained it. And that gives you some trained parameters or weights. And a really interesting thing happens here. Once you have trained a model, you may have started with a massive amount of data, but your trained model is the sum of these parameters or weights. It's really quite lightweight. And so it can make an inference on new data with much less computational power. So the result of that intensive training on the left is a relatively much more lightweight trained model on the right that is just making decisions. And that model on the right is the output of all the effort on the left. And to first order, it doesn't change. So if it's not good, you may have to re-enter the training phase with additional data. Maybe you didn't, it's a great example of a deep learning fail on the NVIDIA AI podcast, where the engineer trained all of his models using a deep learning thing with cats, pictures of cats, because he wanted to cut on his sprinklers whenever his neighbor's cat entered his yard to pee in his yard, creating little yellow spots of dead grass. So he downloaded a bunch of images from the internet to train his model. Now, remember, this is just patterns. It doesn't really know what a cat is. Deep learning doesn't know what a cat, a dog, or a sandwich is. It knows what patterns are and pixels and the data values behind those pixels and the patterns in the pixels. So he downloaded a bunch of images of cats from the internet. He trained his model, and his sprinklers only did, his camera, his Jetson-based camera, only detected a cat in his yard about 2/3 of the time. The other third of the time, the cats would get away with it and they'd pee in the yard. Well, none of us would be right 2/3 of the time. We'd be right 100% of the time. So what was the issue there? And usually at this point, we're in person, and I ask people to raise their hands and guess. And somebody guesses, oh, because all the images of cats on the internet are of cute cats and cute poses playing with balls of yarn. None of them are cats skulking across a yard, finding a place to pee. So he then went and found a bunch more images of cats doing different things, not all in cute cat poses. And then his accuracy went up to way over 90%. Now, it still didn't get to 100%, like it would have been with a human sitting there with a switch looking for cats. But then we know it wouldn't have been 100% for a human either. The human would have fallen asleep sometimes or been looking the other way or something. So I think my big question for you is linear regression something you've all done? Is that machine learning, which many of you probably haven't done? The answer here, again, it's better as an interactive test, but the answer is yes. You probably did it in your probability and statistics class, but you were absolutely creating a model that, given a new X input, will predict a Y value for it. Will it be 100% accurate? No. The results of these machine learning models don't guarantee accuracy. They're not yes or no. They give you a confidence in their assessments. But that means that regression is really probably, I refer to it as the hello world of machine learning. I'm not sure if Luke or John have an even simpler machine learning example that they would call the hello world of it. But to me, it's probably this. Machine learning is in widespread use, but there are also some other methods of classical machine learning methods out there. And these are not the deep learning methods, but the principle is still the same. There's a training phase and an inferencing phase. It's just that the exact algorithms are differing depending on what you're trying to do. And so there's regression methods, there's clustering methods, which I'm a big Marvel movies fan, so I loved it when Tony Stark mentioned using the clustering. Actually, was it Bruce Banner or Tony Stark in their conversation mentioned using the clustering methods for the sensors they were adjusting to detect gamma ray radiation around the Earth. There's random forest methods, Bayesian classifiers, lots of methods for this. And it depends on what your data is like and the characteristics of the data and what you're trying to draw out of it, which is the best method, but they all fall into this this set of things that are machine learning. And sometimes you'll hear us call it classical machine learning because deep learning is a more popular, newer set of machine learning. And so deep learning is a subset of machine learning. It has this training phase and it has this inferencing phase. Luke is going to talk much more about this later. The training phase is very computationally intensive, and it's why, even though the algorithms for this have been around for a long time, it's why it's only really become popular in the last decade, because we finally had enough unstructured data and we finally had enough compute power that we could actually make this useful. It went beyond academic research into truly being useful. And so you see supercomputing companies bragging about their AI performance now as much as their simulation performance. And you also see a plethora of technologies for inferencing and of small, cheap devices you can buy on Amazon that are built with, that have built-in inferencing models meant to do one thing, like infer what you're saying or infer something from an image. The ecosystem for machine learning and deep learning is huge. This is just a tiny, tiny fraction of it. It's 1,000 times larger than this, probably 10,000 times larger than this. but you can think of it as a stack of everything from the compute and storage systems and the processor and accelerators they use to the math libraries and the software frameworks, the management and orchestration layer on top of that, the consumption models and the application use cases. So it is a very complicated ecosystem in machine learning and deep learning that goes along with this boom. And so it's important to have people in your enterprise that are going to track this and really learn it, or to hire a services company that does that. But more and more, we really recommend people have data scientists in their organization that are tracking this. And so I'll just say in summary, machine learning is an approach to AI in which data is used to train a model. It's different from statistics and data mining, although there's some overlap. It's not new, but it's newly powerful due to big data, powerful processors, and optimized algorithms. And it's really powerful when you have lots of data, especially unstructured data. And I think with that, I have no idea how I'm doing on time, but it's time to turn it over to John for a walkthrough of machine learning.
Yeah, we're going to do a quick walkthrough. A little behind schedule, but that's all right. I think I'll still be able to get us through here. I wanted to show you a little bit of a Jupyter notebook that we'll make available for everybody after this, after the talk too. We've actually got it out there on GitHub for folks. And let me share my screen. This one here. All right, so what I've got here is a Jupyter notebook. I'm actually running a product that we have called Omnia that helps me set up a Kubeflow dashboard interface, and then I can just go ahead and launch some containers. And inside of those containers, I've created a few different examples that we can look through. Let me make sure I clear all the outputs here before we get started. And Jay kind of alluded there. What is simple linear regression machine learning? Absolutely. I think it's all of those techniques inhibit some sort of intelligence, right? They're able to take data, bring it down and think a little bit more about what that looks like. So there's a lot of tools out there, but the biggest one in the data scientist toolkit right now is definitely Jupyter Lab. Building notebooks, it's really easy to interactively look at your data, tweak it around, play with.
John,
different models.
can we zoom in on the text, make the text a little bigger?
Yeah, I sure can. You know what else I can do is I can full screen. How's that look? A little bigger?
Yeah, make it a little larger. I think that'll be good.
I've got a huge screen. That's probably the problem there. I can go one more. Let me know what you think of that.
It should be a little better.
Okay. So, like I said, a lot of tools in the data scientist toolkit. Jupyter Lab, Jupyter notebooks, they're key in being able to very quickly, interactively play around with your data, try out different methods. That slide that Jay had of all the classical machine learning methods. These are things that we can do kind of quickly and interactively. So I'm going to try to, in the next 10 minutes, walk you through a real basic notebook that we're going to use Python to load and visualize, prepare a little bit of data. We're going to use a couple of very popular packages. Scikit-learn is one that if you haven't used, definitely take a look at it. It's a great tool for summary statistics and doing a lot of these basic classical machine learning algorithms. We'll use matplotlib and Seaborn to plot and visualize that data. And we'll try to just do a simple linear regression fit and make a prediction from that model that we created. So what the data that we have here is from King County. That's in Washington State. It includes Seattle and some of the other very kind of high-end areas. So you'll see some of these houses are really expensive. And what we want to try to do is see if we can take a look at this this data set of housing prices that has a lot of different information, square footage and bathrooms and how big the lot is and all of these sort of things, and see if we can create a model that would predict the price based on just a simple input. So as you step through these notebooks, you can just kind of click through each line. What we're going to do first is load all of those libraries that I just talked about, Matplotlib, Pandas, Seaborn, and Scikit-learn. And then I have this this data set of the King County housing set. So what you can do is a lot of really neat things to just kind of get a quick view of your data without having to pull up the whole thing, because this is a fairly large data set. It's like 20,000 entries or something. And so if you just do a little head command here, we can just look at the first 5 rows. We see that there's 21 columns. And when I look at this right now, I already see a couple of problems, which is typical in data, right? I've got a couple of 0 values for price. That's probably wrong, I hope. We have some other interesting ones like, I don't know, some have basements, some don't. You can tell when they were built, where they renovated. We're not really sure if Latin long is even important, but we have it in here. And then we have some of these other ones are square foot living in 2015 and square foot lot in 2015. And the idea here is to get an idea if there has been a renovation. Did the place grow or did it shrink? We can also get a little more info about all of these entries. What happens here when we read this in is that Pandas creates what's called a data frame. And inside that data frame, we've got, it just kind of automatically reads the data and assigns it a type. So, you know, we've got some int 64s, we've got some float 64s, kind of a mix and a hodgepodge. And it looks like it's about 3.5 megabytes worth of data. So it's not huge, but it's good to get an idea of how to take a look at this. I mentioned that I already saw some zeros in the pricing, but beyond zeros, another thing that's really common to see in your data is just nulls or, you know, just nothing set. So you have a really nice command here, just is null and give me a sum. And we can see that I've got a couple of them that the bedrooms weren't entered. And I have one that doesn't have a floor entry. So I don't know, it's 1 floor, it's 5 floors. We're not really sure. But now that we kind of have an idea of what that data looks like and what's in there, and we know, you know, that we have a few null sets, that's okay. It's not a lot of them. So let's see if we can just try to maybe figure out what feature in this list will correlate the best with the price. So in Seaborn, a lot of cool commands here. Just quickly build a heat map out of that, and a correlation heat map out of the that data set. And what you can see here is the lighter colors have more correlation. As you can see, this diagonal, those are the matches directly, ID to ID. The darker colors have less correlation. So when we look at this, we go, okay, well, I can probably see that square foot living is at least a lighter color in compared to price. So it's a good place to start. And with a lot of data scientists, you tend to be an expert in your domain. So there is a lot of intuition in where to look first when you're doing some of this data science. And again, some of it is just exploration. And that's why you have these notebooks and interactive playing with them. So we can do a little plot, scatter plot of living by price, square foot living of the living area by the price. And, you know, when I look at this plot, you've looked at a lot of statistical plots before, it looks fairly linear, little bit of noise, which is good. Little bit of weird outliers, like these huge 14,000 square foot houses that have no price. That's a little odd. But what we can do right off the bat is, you know, I say, I'm trained, I think that's linear, but can I just go ahead and print, can you just go ahead and give me a linear regression line? And, you know, just 2 commands here to show each one. We'll draw a regression line for square foot living versus price and bedrooms versus price, because while I said square foot, yeah, but it might be bedrooms. So when I look at these, here's my square foot and, you know, fairly decent regression line. And when I look at versus bedrooms, I can see the distribution looks a little funny, but I do have an okay line that I think is going to help me determine that. Again, some weird outliers. Looks like I have a house that has 40 some bedrooms, but doesn't cost a whole lot. So big questions as to what that actually is. What we can also take a look at is, let me come down here a little bit more. There we go. We can also just say, let me go ahead and take a look, take that square foot living and because I said the bedrooms was fine, but I think square foot of the whole living area is the best correlation. So we can just create a model, a linear regression on that, and do a fit. And then what we can do is we can say, can I predict what the price will be based on square footage? So I put in 12,000 square feet and give me a prediction. And the answer ends up at 323 million. 3.2 million. But if we go back and look at that data, the actual data, we know that the real answer is about 60,000 higher. There's a lot of things that could go wrong here, but again, this was just a simple linear regression. So we can take a look at a lot of different models to do this as well. Of course, to note, 60K lower than the actual price would be not all that great for a seller, but would be great for the buyer. So, okay, linear regression, that's fine, but let's take a look at some of those other classical machine learning techniques that we kind of talked about. Let me make sure I clear these out again too. I was just running this earlier. So, okay, we did the linear regression and that was fine. We used scikit-learn. We know that we can see that's a pretty simple and efficient tool. You learn a handful of commands and you can be really powerful with your data. So in this notebook, what we'll be doing is, again, loading that data, visualize it, and then we'll use scikit-learn functions to look at important statistics or things that we think are important. We'll still use matplotlib and Seaborn to plot and visualize the data, but this time we're going to go and fix those null entries. We're going to fix those zeros, and we're going to convert this into a suitable form for classification. I'll describe what that means when we get down there. We're going to divide the data set into train and test sets, and then we'll scale those training and test subsets. And then we'll run a random forest, we'll run a support vector machine, and we'll run a basic neural network. And what we'll be able to do is very quickly run, we just did linear regression. We'll quickly do these three. And then, within 10 minutes, you've just run, you've been able to look at a lot of data and run a handful of different classical machine learning techniques very rapidly, right? That's the really cool thing about doing this interactively and using the notebooks like this is you can take advantage of all your horsepower on the back end, but you can do it interactively and really get some insight from your data. So same thing as before, we're going to import all of these libraries in just standard Python stuff. We're going to read that data set again as pandas datagram. And what I can do first is, again, I want to poke around. I want to look at that data. We can look at the shape. I see there's 21,000 rows and 21 columns. If we look at we just print out the first couple of entries. We saw this before. We've got some IDs. We've got a timestamp date that probably doesn't help me. I've got a zero price on a few of them. And if you remember correctly, we had a couple of nulls in there as well. So let's again just go ahead and look at that heat map. And again, the same thing that we saw earlier before, but this time, instead of using all of that data, let's clean some of it up and let's pull out a few of the things that we don't think we're really going to need, right? And what I say when I don't really need, when I'm looking at price along here, I'm going to start picking off the categories that are really dark. Things that are just clearly don't have any correlation according to this data set. So ID, perfect one, very dark. We'll drop that. We'll drop square foot of the lot. We'll drop the condition, the year it was built, the year it was renovated, because none of these things matter in Washington State when the housing prices are so high. The zip code, it's all in one county. So there's probably only one or two zip codes that are in that county. We're going to drop off the square foot of the lot in 2015 because the lots rarely change size, but sometimes the houses do. The other thing we're going to drop is that lat and that long because they're all in the same county. It clearly doesn't have any correlation to price because they're all in the same area. And we're going to drop date as well. Because again, those are just dates from 2014 to 2015 of the prices of those houses. So some really neat quick commands here that we can drop right out of the list in a single command. You create a list of all of the columns you want to drop and do a housing.drop, and you can just do it in place. And now we can draw a heat map, and it looks a lot simpler, I think, at least to me. I've removed a lot of the features that I don't think matter, and now I can get a better view of my data. Now I have 10 potentially useful features. We can take a look at what that data looks like again. So there's the head, and you can see we changed. We no longer have that ID. We no longer have some of those other ones that we dropped out. We're just these 10 factors. So we can do the same thing like we did before. We can do a scatter plot of the bedrooms versus price. And when we drew that regression line, it looked pretty linear. But if you look at this is definitely not a normal distribution, right? It's skewed towards lower priced houses. So we can plot a histogram of that and print out the mean being about 500K, a little over. But we can see, again, this line is skewed over here. We'll quickly go through here, and again, let's look at how many nulls we have. Again, there's some bedroom nulls, some floor nulls. We can just fill those in. For instance, we could fill in any of these with just a 5. Just a, arbitrary. Bedrooms are 4. Let's go ahead and fill all the, fill all those bedrooms in with a 5. And now I can see I replaced all of the nulls with a 5. So now I don't have any nulls in my data set. How about, like I said at the beginning, I had a couple of housing prices that were 0. You can quickly pull that out. Hey, show me anything where price equals 0. Here's the 4 values. And since there's only 4, I mean, it's not a big deal. We could probably just drop them out. We could use a regression model to put a price in there. We could use mice to put a model in there, but a lot of that's probably not worth all the effort. It's a lot easier to just drop in a mean at the beginning, because that's probably simple enough to handle this data. So let's go ahead and take a look at that mean here. We can replace all those zeros with the mean. Remember, and then we'll go ahead and take a look at that. So here I just did a price replace in place on that same data set, print it back out. Now we've got the mean in there for those zeros. But when we classify, what we want to do is we need to assign each row to a category. So I need to convert that price column into a label, and then assign, and then what I want to do is I want to find the houses in the top 50% of the market, so that I can roughly divide that data set in half. Because again, we're saying our mean is about 500K. So I'll just create 2 bins. I'll make a group name too low and good, at least at what I think is too low and too good and good. And then we can just very quickly use pandas to cut those into bins and then show those value counts. So here I've got 12,000 of my entries are considered to be too low. About 9,000 of them look good. And that's nice. Oops. Oh, what did I do? That's okay. I'm just going to skip ahead here because I'm running out of time. If I take a look at that that head again, now I've replaced those with good and too low. But the problem with that is that's fine for me visually, but when I put this in the computer, it can't determine what's good and too low. So you just need to encode that into a numerical value. So we're just going to make a 0 and a 1, and very simply just use this label encoder and fit that price on there. So now my too lows are represented by a 1 and my goods are represented by a 0, and we can plot those out where you can see, again, it's not a perfect split, but let's see if I want to split this out to a test and a trained data set. This should be okay based on the data that we have. So what I also want to do is one of the things that important about data is data types. We saw that there's some were ints, some were floats. Most of these routines require everything to be in the same type. So if we look at that, I got floats and ints, and we can just really quickly just go, hey, turn everything into a float, show it to me again. Really simple, really easy. Same thing on the y-axis, turn everything into a float. And then let's split that data. Very simple command that you have right into scikit-learn, train test split, so that it'll pull out half of it for a training set and half of it for a testing set, so that we can build our models based off of that. So we take a look at that, and the distributions look good. The one thing that we always need to do too is scale that data. And remember, if you scale your training set, don't forget to scale your test set as well. And then here I've got 3 different models. We've got a random forest, we've got a support vector classifier, and a neural network. I'm just going to fire all 3 of these off, and they'll take a second to run, not too long. And then we've got some nice statistical tools out of scikit-learn so that you can print a classification report of how well that model performed, and the confusion matrix, so you can understand a little bit more about how many false positives and things that you found in that data. You get an F1 score to show you how well that the precision and the recall work. When we look at a random forest, we see we're in the 80-ish %, and that's pretty good. When I look at the support vector classifiers, maybe a little bit better of classifying the goods. Not much though, and about the same for classifying too low. And then in my neural network, I got a little bit of increase, again, a little bit more than a little higher score than the previous ones. And what this allows me to do again is just really quickly look at my data, get an idea of what's going on, run some simple regressions, some simple machine learning techniques, and then we can start to move on from there into more complex workflows. We can share these notebooks with our collaborators. You can publish them on on GitHub, and that's kind of the really neat thing about this. So I did go a little bit over my time. I'm going to stop now and allow some time for a break. And Luke, what time do you want to start back up then? I bit 5 minutes into our break time.
That's all right. Let's take a 10-minute break, everyone. We can come back at 9:45 Central Time. That would be 3:45.
Okay. Thanks for the first session, guys. Yes, we'll reconvene. That'll be 3:45 in 10 minutes time here.
All right.
All right. We'll see you in 10. There were some questions that I see in the chat while we're waiting for Luke to jump back. Is there an industrial standard or preference to divide data for training and testing? So not really an industrial standard. I think a lot of it right now is still, there's still a lot of intuition, kind of as I was pointing to, when I'm looking at housing costs, not being a real estate expert, I at least know that things like square footage and such is good things to look at. And when I split that, the idea is to get it as close as we can to 50-50, but that's not always necessary. It can be in the 70-30 range for your training versus testing. But I think you want to split it as evenly as you can, or at least split it on the mean. And we will have, I think we'll have another, if we don't get to the actual notebook, we'll at least point you again to it. We have another one for a deep learning deep dive to kind of cover, the basic MNIST, handwritten letters and numbers classifier. And, some of these tools, like I said, I've been doing AI for a long time, and we used to write some of these MNIST examples in C. And then it was like, oh, cool, now we can write this in Python. It's quite a bit easier. And now we have these high level languages, like Keras to sit on top of TensorFlow that really bring it down and make it really simple to do a lot of these basic classifiers and build neural networks and all that sort of thing. So it looks like Luke's back. I'm going to let him talk about deep learning when he unmutes.
Life in Zoom meetings. All right, so I hope everyone had a good break. We'll get started with a short introduction to deep learning, and then we'll focus a little bit on some of the interesting work we've done in scalable deep learning at DELL. And if we have time, we're going to step through a notebook that shows a basic image classifier using neural networks. So what are neural networks? Well, they're part of a group of what we call meta-heuristic techniques called, in the category of nature-inspired computing. So we're looking to nature as inspiration for being able to process data in a way that doesn't fit easily into a standard algorithm. So we can't define a very deterministic algorithm that can guarantee an optimal solution to a problem. And so for these very complex problems, we look towards nature for inspiration. In this case, we're looking at the brain. And you can see on the left, there's an image of a brain stain image. And you can see different neurons and axons and dendrites. We try and mimic that architecture in a computational way. And we do that with computational nodes or neurons interconnected by data paths. And so you can see on the right, a basic example of a neural network has an input layer, a couple of hidden layers, and an output layer. And when we put enough of these input layers and hidden layers together, we can start to do very interesting things. And in image classification, one of the interesting techniques that has significantly improved performance of these types of models is the idea of the convolution, where we're taking filters or small subsegments of the image, of the input space, and we're extracting interesting features or information from them. And we do this in a set of successive layers that allows us to extract more and more abstract features before we flatten and classify. And so you can see that in this example, there's actually two networks here. There's a convolutional network, and then a feature extraction network, and then there's a classification network. And this is very important in a lot of these image classification problems because it allows us to do something very interesting. It allows us to take the classification part of the network off, attach a new classification component, and retrain either all of the layers or just the classification components, and build a neural network that's actually in a completely different domain. And we see this over and over and over again in all sorts of different examples where we take a neural network that's been trained on something very standard like ImageNet, which identifies dogs, cats, sandwiches, airplanes, and things like that. We take the classification layers off, we add new classification layers, and retrain those classification layers to do something interesting, like identify pneumonia or emphysema in chest x-rays. We don't have to retrain the whole network. We can just retrain the classification components because the first part of the network is about features and abstractions, and those don't really change in the way we process image data. So why convolution? Again, it's another nature-inspired concept. We are looking to nature to help us figure out what sorts of techniques work best for a lot of this data processing. And so we look at the way that the eye functions, either the mammalian eye or the avian eye, and we can see that the retina is actually covered with these photon receptors, this huge receptive field, and the connections to the underlying neurons is actually in fields. So you see these overlapping sets of receptive fields at the back of the retina, and this is exactly what we're doing with convolution. We're building these overlapping abstraction and these feature extraction fields. And so you can see an example here where you've got a convolutional neural network. The images of a fully connected network, but in a convolutional neural network, you can see that the input images on the left are of people's faces. And what they've done is they've done an activation image of each of the internal layers to see kind of which neurons are firing at which times. You can see over the course of successive layers, just looking at more and more complex features. First looking for things like contrast and edges and curves, and then starting to peel out individual facial components, and then starting to put together entire faces. And this process is computationally intensive. It takes an enormous amount of time to train these models to any reasonable level of accuracy. So what we do is we parallelize the process with high performance computing. And by parallelizing the training process, we can improve the time to solution significantly. And we do this by two means. We can either do it with model parallelism, where we spread the neural network across different compute hosts, or we do it with data parallelism, where we spread the data set across different hosts. In the case of data parallelism, we can make a replica of the neural network on each compute process, spread the data out, and then we exchange information about the success or failure of the network in classifying those images correctly amongst the different compute processes, and then train all of them together as one set. And this allows the neural networks on each compute host to stay the same while training on much more data than would be possible on a single machine. And so this allows us to do really interesting, complex sorts of workloads across any number of different accelerator types, any number of different server platforms. We can take models. In this case, we're actually taking a neural network that was originally trained on ImageNet and using it to detect pneumonia and emphysema and several other thoracic pathologies and chest x-rays. And retraining this network can take a significant amount of time. It takes about 5 days on an unaccelerated system. But if we use scale-out parallelism, use entire supercomputers to speed up the training of that network, we can actually get it done in a matter of minutes. Our fastest time to date is about 7 minutes. And not only that, we can start to look at improving the accuracy of these models, because we're unsure when we begin the training process what the search landscape looks like. We have no idea what the search space is. And we only get glimpses of that search space when we compare the inference result, the image classification result, to the ground truth. And so it can be difficult to search this space and find a more optimal configuration of parameters for these neural network models. So the faster you can train, the more images per second, the more data objects per second you can train across, the more likely it is you will find a higher quality answer, because you're doing this search across the search space looking for these optimal parameters. And so by scaling out the training and improving the time to solution, we can also improve the accuracy by allowing the system to search the space more thoroughly. And so we actually did a comparison to an initial paper that was published by Stanford University on this exact same model. And we were able to improve the accuracy of the model in 10 of 14 different thoracic pathologies against the baseline model that Stanford presented, just by scaling up the training and going a little faster. It allowed us to search the space more effectively.
Luke, there was a question about splitting the model and as well as the data. Can you talk a little bit more about what you mean when you say splitting the model?
So like I said, there's two different types of parallelism. There's data parallelism, which is what we're doing here, where we split the data set, and then model parallelism, where we actually put different regions of the neural network on different memory segments and different process segments. And that's something that has to be done for extremely large networks. So if so we hear about these really large networks that have many millions or billions of parameters, like GPT-3, for example. GPT-3 is a multi-billion parameter model. It's about 127 billion parameters. It just doesn't all fit reasonably in a reasonably sized system, in the memory space of a reasonably sized system. So you have to spread that model out across multiple computers. And when you do that, the process of making an inference, for example, in that neural network, involves multiple computers, whereas if you're doing data parallelism only, the neural network can fit inside of a single system. And so you can do the entire inference component on a single machine. Does that answer the question?
Well, I think it did for me. Let's see if yep, it did for them too. Good.
All right. And so we can also step beyond the traditional neural networks. And normally what happens is when you build neural networks, there's a data scientist that is creating the neural architecture for these particular models, and then you train against the data set in order to fit the parameters to the input space. But there are ways to let the computer do the design part, the neural architecture search. And we're going to talk about it a little more at the end when we talk about future techniques. But just to point out that it is very possible to offload not only the training of the neural network to a machine, but also the design of the neural network to a machine. So you can actually do a lot of these interesting components, these interesting designs in neural network architecture through a computational search, as opposed to having a person handcraft each of these neural networks. We've done some work with McGill University on an interesting project where we're actually using neural networks to do reverse mapping of functional MRI images, where we give the neural network that activation map, and then we have the neural network infer what the activity or task the patient was being asked to perform, what activity or task the patient was being asked to perform at the time the image was taken. And so there's a really interesting project that showed very good accuracy in both identifying motor tasks and working memory tasks. And it's something that goes beyond the traditional two-dimensional image classification. We're looking at 3D volumes of the brain. In this case, they're very large. They're multi-tens of gigabytes each in many cases. And so being able to identify, to process a type of data requires a fair amount of parallelism, but it's something that is enabled by this mixture of high-performance computing and deep learning. We've also done some work in language translation, and in this space, there are models like GPT-3, which are based on the transformer architecture concept. This is a type of neuron that type of neural architecture that provides context. It allows the neural network to understand what it's processing now in the context of what it processed before. And this is not true for convolutional neural networks. Convolutional neural networks are what we call stateless. So the image you pass through is not influenced by the image that was passed through previously. So if you recognized a picture of a dog in one pass through the network, and then you pass an image of a cat through, there's no residual leftover context from the dog that went through before. So in these transformer models, you do have context. And this is very important for language because it's very difficult to translate language without context of what was said in the words immediately following and what is being said in the words immediately after. And so these particular networks provide a state-of-the-art classification, translation accuracy, but they're difficult to train. And the reason they're difficult to train was a problem algorithmically with the way the frameworks handle these types of operations. And so we actually worked with a large collaborative group at Uber and Amazon, Intel, and Surfsera to identify the problem and fix it. Now these types of models can be scaled up significantly, using hundreds of compute processes or thousands of compute processes. We can train these models in a few hours as opposed to a month or more. And so all of this goes back to just being able to train these neural networks to do really incredible things in a reasonable amount of time. We've also done work with voice synthesis. And in the voice synthesis space, it's very difficult to build out models that can actually replicate human voice. And normally what happens with these sorts of models, with these voice systems, if anyone's ever been stuck on a call tree for minutes or hours on end, they're usually built by stitching together phonemes, which is small segments of sound, and they stitch them together to make it sound like the computer is speaking, but they always sound very artificial. They're very synthetic because the phonemes don't blend together very well. in many cases. And so we can build neural networks that make this this translation, this narration of text through an artificial voice. And again, a very long process. It actually takes about 47 days to train one of these models. But with a little bit of parallelism, we can get it down to a little over 2.5 days. And so if the sound works here, I'm going to try playing for you a clip of this neural network teaching itself how to speak. And what we've done is we've looked at, we've had the neural network at different points in the training phase, at different epochs. And epoch is one pass through the training data set. So at different epochs, we're having the neural network say the same phrase. And we've recorded it and we've stitched it all together so that you can hear what it sounds like when the neural network is learning to speak. And so just think about it in the context of, you know, how you would normally hear a child learning to speak over the course of many years. And remember that this happened over the course of about 2 days. So I'm going to go ahead and play the clip and hopefully you can hear the audio.
Hello world, hello world, hello world, hello world, hello world. This is my voice.
And hopefully everyone was able to hear that. If not, we'll send the slides out with the audio clip after the session. But you can hear how it learns. It goes from basically random white noise to fully functional, fully formed speech over the course of many different training sessions, training epochs. And it's a really interesting process because we're no longer working in the basic classification space. We're translating from one medium to another. We're translating, in this case, from text to audio. And we can see these types of translation tasks in all sorts of different neural networks. Later on, when we talk about future techniques, we're going to talk about image generation. We're going to talk about reinforcement learning and ways that we can build more complex decisions, more complex outputs with these neural networks, more complex than simple classification. We've also been working with the U.S. National Cancer Institute to explore the effectiveness of convolution as a way of reading the codons from RNA sequences in the human papillomavirus. So this is a project that's been going on with them for several months now, where we're actually using a convolutional neural network to extract these codon features and then use those features to predict whether a particular virus is likely to result in cancerous tissue growth. And with just a few thousand training samples, we've actually been able to get the accuracy of this model up to a little over 76%, which is a very good result. We're hoping to get it higher with more training data. But the eventual idea is to be able to look at the neural network. So it's a very simple neural architecture. We don't have a lot of complex layers in it. And the goal is to be able to look at the activation visualizations of these different neurons and figure out which particular regions of the RNA sequence are actually leading to a positive classification. And by doing that, we can start to look back at the RNA sequences and see what particular regions of the sequences are leading to that positive classification. And so many people will say that neural networks are black boxes, that you cannot interpret what's going on inside of them. That's not true. The more complex they are, the more difficult it is to determine what it is they're actually doing, to explain how they're making their predictions. But it is possible to look inside the neural network and use information about the firing patterns, the activation patterns, to gain insight into the reasons why it makes a particular classification. That's an important space in coming up in the research, is being able to explain our decisions. It's going to be very important for being able to trust and verify the classifications, the results of these decision systems going forward. And one last project I wanted to talk about really quickly. This was published in the the proceedings of the Neural Information Processing Systems Symposium in December, the collaboration between DELL and Carnegie Mellon University and a few other collaborators, where we're looking at using neural networks to replace simulation. So in this case, we want to be able to approximate turbulence in fluid flow by using a neural network as opposed to doing a direct numerical simulation. And the reason we want to do this is that numerical simulation is expensive. It can take, hours to do a very short-term fluid dynamics simulation, and that makes it difficult to work in the design space, where if you want to configure a car or an airplane wing or something like that, you may have to run many hundreds or thousands of simulations. But what we can do is we can replace that simulation, that forward simulation, with a neural network, and we can get that answer in seconds instead of hours. And that allows us to more thoroughly explore the design space and focus on those outer loop questions, the ability to make those larger, more complex decisions where the objective function is the result of the simulation and not the simulation itself. And with that, we're going to step through another notebook. We have a notebook for doing image classification on handwritten digits. So this is the technique that sort of inspired it all. This is based on the work that Jan LeCun did at Bell Labs, where he was trying to figure out a way of automatically identifying zip codes on handwritten letters. So this is kind of the example that started the modern deep learning revolution back in the late 80s. And so we'll take a step through this notebook. I mentioned it before. You can get all of these notebooks in the GitHub. I put the link in the chat, so if you want to, you feel free to go grab them. And we're going to be using a deep learning framework called Keras. And what Keras does, it's a high-level abstraction on top of TensorFlow that allows you to focus on the neural network design rather than on the lower-level interconnection between different vectors and tensors. And so that allows you to focus on building a layer-by-layer network in a very simple, straightforward way. And so what we're going to do is we're going to build a deep neural network called a multi-layer perceptron. So perceptron is a simple neuron that takes in multiple inputs. It multiplies each input by a weight. It sums them up, and then it passes that weighted sum to an activation function, which will or will not fire depending on the value. And so the first thing we do is load all the appropriate Python libraries. You can see here we've imported Keras as well as different subsets of it. We're going to borrow the MNIST data set. We're going to use a sequential model. We'll use a couple of different layers. We'll use dense and dropout. And then we're going to use a root mean squared optimizer for doing the optimization. And so when we build this neural network, we're actually looking at building a few different layers of different sizes. And in order to build those layers, we have to know a little bit about what the values are going to be. So the output layer is actually based on classes. So in our case, we're wanting to classify 10 different digits between 0 and 9. And to do that, we need 10 different neurons in the output layer. That's the number of classes. So there will be an independent classification for each of the digits 0 through 9. We also need to have the concept of a batch size. That's the number of images we want to process simultaneously. And we do this in order to improve computational efficiency. If you were to just pass one image through at a time, you're typically not effectively utilizing all of the compute hardware at your disposal, especially if you're doing an accelerated neural network training run with a GPU. So adding more training images to a single batch allows you to more effectively utilize the computational resources. So in this case, we're going to set a batch size of 128. And the epochs are the number of times we will repeat the entire training data set. Typically, neural networks do not train on a single pass through the data set. You have to train multiple times. So you have to see the same image many, many times in order to get a reasonable value. And in this case, we're going to go through the training data set 20 times. And so once we've done that, we can start actually building the testing and training data sets. And we will use Keras' built-in dataset helper functions to do that. So they provide in this data set, the data set that contains about 70,000 images of different handwritten digits. They're all grayscale. So what it does is it will download all of those images from the internet, put them into local memory. And then what we're going to do is we're going to split those up. So we're going to load the data and simultaneously split them into training and testing. And what we do here is reshape them so that they have about 60,000 training data elements. There's 10,000 testing. We're going to make it all float 32. And then what we do is we normalize all of the input data. So what happens is all of the data is in image format. So every pixel has a value between 0 and 255. And we want to normalize that to between 0 and 1. And the reason we normalize data in that way is to reduce the probability of vanishing or exploding gradients. So the larger the range in input values, the more likely that as you pass through the neural network, you're going to end up with error differences that are far too large to train on. And so what we do is we normalize these values to between 0 and 1, as opposed to using 0 to 255. And that allows us to potentially avoid the vanishing and exploding gradient problem when we train. And so the next step is to set the labels for binary classification. And we do this because we ideally in the training data set, all the images are labeled with a one-hot encoding. They either are that digit or they are not that digit. So there's no real room for interpretation in the training data set. We know exactly what the digits are. And because we know that, we can use binary classification for each of the different neurons in the output layer, each of the different classes. So what we do is we set the data to be binary classification for each of the classes. And that allows us to build a one-hot encoding where you have a vector that has a single 1 and the rest of the elements are 0. That means that if it's the number 0, then the first element in the vector will be 1, every other element will be 0, because it is definitely not the digits 1 through 9. It's definitely the digit 0. And so now we'll begin the process of actually building the neural network. And when we build this neural network, again, we're using this architecture called a multi-layer perceptron. We're going to build it out of these dense layers. Dense is the term in Keras for a perceptron. And in our case, each neuron in the dense layers will be activated with a function called ReLU, or the rectified linear unit. And the reason we use these activation functions that have these nonlinear characteristics is we want to introduce nonlinearity into the model. We want to be able to more readily change the input or the output characteristics of each neuron. And this helps us to, again, deal with the problems of the exploding and vanishing gradient. And so the rectified linear unit function looks exactly like that picture. And anything that's positive just returns the value. So it's a linear function on the positive side of the input. On the negative side of the input, it returns 0. So this allows us to add some nonlinearity into the space, but it does it in a very computationally limited way. So in the past, when we would build neural networks in the 80s and 90s, we would probably use something like a sigmoid or a hyperbolic tangent to provide that nonlinearity. But trigonometric functions are very difficult to calculate. They're actually done in the computer by lookup table in most cases. And so to simplify that process computationally, we switched to a simple to compute unit. The rectified linear unit was the perfect candidate for that. And what we're going to do is we're also going to add these special layers after each dense layer called dropout. And dropout will periodically eliminate those neurons from adding to the subsequent layer. So they'll just pretend that those neurons don't exist. And so what that does is it adds additional nonlinearity, and it allows us to make sure that we're finding good solutions in the space. And it does it at a random interval. So dropout in this case, if you look at cell 6 there, you can see that we're using a 20% rate of dropout. So 20% of the time, the value of that neuron will be zeroed out during the training phase. And that's all done at random during the training process, which can make it difficult to replicate. You know, it's almost impossible to train the same neural network in the exact same way twice. So you know, if you train the same neural architecture on the same data 2 different times, you will end up with 2 different neural networks. And it's just something we have to accept about a lot of these meta-heuristic techniques, is that they rely on randomness. They rely on probabilities to do most of their work. And so by understanding that there's going to be some non-determinism in the system, we can build better solutions to these non-algorithmic problems. And so we build a model summary. You can see here that we're saying that we're going to build a sequential model. And then what we do is we add layers to this model. So we added a dense layer with the input shape of 784. And the reason the input shape is 784 is because each of our inputs is a 28 by 28 pixel image. And so we're going to flatten that image into a 1-dimensional vector. And then we're going to have layers, 512 neurons in a dense layer, followed by dropout, followed by dense, followed by dropout. And then the last layer is the number of neurons in the last layer is the number of classes that we want to classify in. And so you can see here that last layer has num classes as the number of neurons. And instead of using the rectified linear unit for that activation, we're going to use softmax. And softmax will approximate a probability distribution between 0 and 1. And so we construct this neural network. You can see we've got a total of about 670,000 parameters. Every single one of them is trainable. And if you do the math, and I left the math in the notebook there, you can see where we get that number from. And that's from the various connections between the neurons in each of the successive layers. And so if you look at the total number of connections between layer 1 and layer 2, and then layer 2 and layer 3, you can add all that up and you'll get exactly 669,706 parameters that are tunable. So each one of those numbers is changed during the training process. Every single one of those parameters is tunable. And so that's why the training process can be so computationally expensive. This is basically the simplest neural network that we can build, and it still has an enormous number of different adjustable parameters in it. So the next step is to compile the model. And in this step, what we're doing is we're telling Keras, we're telling TensorFlow, okay, we're going to take that neural architecture, we're going to assign a loss function for the optimizer. In this case, we're going to do categorical cross entropy. And that's because we have more than one class. If we only had one class, we could use binary cross entropy. But in this case, we're going to have multiple classes, so we need to do categorical. We're going to use root mean squared as the optimizer, and our metric is going to be accuracy. And there are multiple metrics. You can look through the Keras documentation to see all the different metrics, or you can define your own metrics for the optimization. And so finally, we get around to training the model. And this is where we're actually going to pass the training data into the neural network, see how well it performs, and then back propagate those errors through the neural network in an attempt to tune the parameters, all nearly 700,000 of them, in such a way that we get better accuracy the next time we see that image. And you can see it's going through the training process now. it'll do this 20 different times. And you can see that the accuracy started out at about 86%, which is pretty good. And as we go along, you can see the validation accuracy on the far right steadily increasing. Sometimes it goes down between epochs, sometimes it comes back up, but you can see we kind of settle into a steady state right around 98% accurate. You can see at the very end, the validation accuracy is 98.5%. So the validation accuracy is the accuracy on the testing data set, whereas the accuracy in the middle column is the accuracy on the training data set. So you can see it's significantly more accurate on the training data, but that doesn't really mean much because it's seen the training data before. It knows exactly what the answer is. The real value in a neural network is being able to accurately identify things it has never seen before. And that's where the validation accuracy comes in. And so we'll let that retrain one more time. And then what we can do is we can score the final model, and we can use the scoring function, the evaluate function, to build that score for us, and it'll do it completely on the testing data set. If anyone has any questions, please feel free to jump in. All right, so we're almost done with this training phase here, and then we'll see that it will score. We can see we get about 98.43% test accuracy. You can see it's slightly different than the last time we trained. The last time we trained, we were at about 98.5%. This time we're at about 98.4%. And that's because when you train, 2 successive training runs will never result in the same model. All right, so let's try and do a prediction. So we'll display an image here. We can see that this image is of an 8. All right, so hopefully when we make the prediction, it will show us that it's classifying that as an 8. So let's take a look, and sure enough, it's 100% confident that this is an 8. And so thankfully that's the right answer. When you download this notebook for yourself, you can change that image. So you can change that, to some other image, and then rerun the section of the notebook. You see there you've got a 2, and when we do the prediction, sure enough, the neural network thinks that's a 2. So you can see how we can very quickly create neural networks to do a wide variety of useful tasks. This is a very simple example. It's kind of the hello world of deep learning. But I went over a few examples of how more complex neural networks can be generated to do more interesting sorts of classification and non-classification capabilities. And we'll talk a little bit more in the future techniques section at the end of the talk about where neural networks are going now and the types of things you can do with them that are far more interesting than simple classification. Are there any questions on the deep learning section that I can answer?
Now we all know a little bit more. We're all a little smarter.
That's great.
All right, let's dig into something that I really love, actually. I mean, AI is awesome, HPC is cool, but the real neat stuff is in containers and orchestration, and how that world is rapidly changing. I've worked with supercomputing centers here in the United States and with folks all around the world, and with private industry. And the one thing I can tell you over the last 20 years of that is they're all remarkably similar. They're huge homogeneous systems. They're usually purchased all at once. They're stood up, they run for 5 or 6 years, and then they recycle it, throw it away, and buy a new one. And there's a huge heroic effort that goes into maintaining those systems by the system administrators and by typically large groups of HPC specialists that tune and build all these libraries and build all of these applications and build all of these hierarchical stacks of container, of a compiler, MPI application in a multitude, multi-combinatorial explosion of different options. Well, we've got a new modern way to help that out, and that is in containerizing those workloads. We've spent a lot of time on figuring out how to, have reproducible results, how to make sure that you're always using the same version when I pass it off to my research group, that they didn't just go download something from source and build it on their own. Now I can actually containerize an entire application, all of the libraries, all of the executables, all right into a single container. And while you're probably familiar with Docker, because that seems to be the de facto large standard that kind of took over in the beginning, there's actually quite a few other containerization technologies that are really taking off right now. Containerd looks to be one of the possible defaults for the next versions of Kubernetes, as well as Cryo. And in the Red Hat world, they created Podman as a way to run rootless containers, which was a big problem, security issue in HPC and sort of government-sponsored systems that didn't really want to let people have root on those systems, and for good reason. So we've seen Podman, and this big S in the middle is for the Singularity from Scilabs. And what they did was they were able to create a runtime that can handle any of these runtimes, but it does have to convert it into a giant flat file. So it's worked really well as a shim to get containers running on today's supercomputers. But what I want to talk more about is the ecosystem of how we can use these to create reproducible and portable results, and talk a little bit about the differences that we're looking at in AI and ML versus what we used to look at for all of our simulation and modeling. So typically in a simulation and modeling setup, we have what we call a run to complete code, right? We have a simulation that will, do a drug discovery or show us weather or, airflow and things. And these all have really strict time domains, right? There's a start and an end, and we get an answer at the end. Well, in AI, we're using inception servers, persistent services, things that are just sitting out there running on your cluster that other people are taking advantage of. The model is a little different, right? Now, if I create a really great model, like Luke was talking about, to replace some of my brute force calculations for airflow, and I have this ultra optimized neural network model, I don't want to just keep it for me. I want everybody else on the system to be able to use that too. And the way that this has grown is that, now we create models and we say, oh, I'm just going to throw that model up on the server. And whenever you need to do that calculation, just hit that IP address or hit that web interface or hit that API. And that's been complex in adopting in some of our modern supercomputing systems. So what we try to do is help people understand that there's less work for the admins now, less work for those HPC specialists of creating all those software stacks, compilers, libraries. And the other really neat part is all of the vendors have started to create their own optimized containers for these frameworks, for the AI ML DL framework. So now I don't necessarily, I still absolutely have to have a handful of experts in my lab, but they don't have to spend all their time building software and configuring it for the rest of the users. Now we can just say, oh, you're doing TensorFlow on the GPUs? Well, go grab the NVIDIA container from NGC. You're using something like a Xilinx FPGA, you can pull containers directly from their marketplace that's already optimized for their FPGAs, and we don't have to worry about all of that. So containers are really a good way to pull down a lot of that complexity of software stacks and really simplify things. And on the orchestration side, of course, it's Kubernetes is king still today. There were others that had tried, and this is really kind of percolated up to the top. It's a very simple resource manager for container orchestration. And what that means is, this is, if you're familiar with your supercomputers running Slurm, which were batch scheduled systems, This is a lot of what this does is it will schedule your work for you, but it does so much more than just schedule your job, right? We have lots of layers of software-defined networking, layers of different capabilities that we can add to the system, and different ways to interact with our systems in a more modern way. We can, very easily schedule all of the available resources, like things that you've seen. But what's neat here is that you could be running Kubernetes on your workstation or your laptop and developing code, and then push it back to your large scale bare metal or cloud infrastructure, and you don't have to change a whole lot, right? If I wrote a code here and I compiled it here, I can now just take that container and move over to the next center, or move out into the cloud, or run it on my laptop. And this, helps to reinforce that distributed compute model, and is really focused again on microservices. And that's what I'm going to talk about a little bit today, to give you an idea of what that means to have a containerized application inside of Kubernetes. And always feel free to stop and ask any questions. Happy to answer any of them. So a real basic example in Kubernetes, an application like an inception server, something we were talking about earlier. So I have an inference model that is highly optimized for identifying cats, dogs, and sandwiches from an image, let's say. Well, that app needs to be able to run somewhere on your system. And the basic pieces of a web app is something like, maybe it's a PHP server, a web server running, and a real basic index.php, something that very simple code. And 10 years ago, we would have stood up would have built one system just to run this web server and host this one application. Well, now the idea is that what we'll do is we'll contain that web server inside of a container. We'll wrap it up. And what we find is that, of course, networking is hard. Like I said, 10 years ago, if I were to build this, I would be building a standalone server. I would install the whole LAMP stack. And then if I wanted to run more than one application out of that LAMP stack, networking is complex. I have to figure out, what can use what ports, and what rate can I actually allow to accept. And these are the things that Kubernetes actually handles for you. It will go ahead and schedule, distribute, load balance where you have to. And the other cool thing here is that if you're launching your container inside a Kubernetes instance, if that node were to drop off, die, or gets turned off, the Kubernetes manager recognizes that node is no longer running, and will take whatever services were running there and migrate them to another available piece of hardware. Now, the other thing, though, is that data does have to live somewhere, right? So we'll get into that. What we do with in Kubernetes is we have our web server with our little application in there. We have that wrapped into a container, and in the concept of Kubernetes, that's wrapped into what's called a pod. Those pods, they can be any number of containers, right? In this instance, it's just one container, but we could have several. And these are all connected through what's called an overlay network to the rest of the environment. So Kubernetes just handles all of that software-defined networking for you. So we don't have to really think too deeply about the complexities of where this is running and what IP address it's going to get and how that's going to move if I need to migrate. And we can also very quickly with when we write things into pods is replicate them. And so we can scale up or scale down any of these applications that we're running in our system. We can also use replication to do rolling updates, which is really great, because now I can say I have a service out here that's the cat dog sandwich model, but man, Luke just wrote a really good model, and it's just blows the other one out of the water. So what we can do is, instead of taking down the services which might be used right now, we can actually just we can say, well, let's replicate what we have there and let's do a rolling update. So now we'll do an install of our new model, and as that model becomes available, we'll start scaling down the old one. And that way we reduce the amount of downtime on the system while we're continuously updating. And that's where we come back to this, continuous integration, continuous development. A lot of these things aren't written once and then deployed for a year. A lot of these models are constantly changing. So what else does Kubernetes do for us in this sense? Well, they can provide a lot of the services that we need. They can do all of the load balancing and discovery, provide me an IP address. We can find pods by specific selectors. So it's really a nice method for being able to deploy an application and then very quickly be able to recognize, oh, that application is really getting hit by too many people. We need to start making that higher availability and replicate that service. I mentioned that the data's got to live somewhere, and of course we've got lots of different disk interfaces for Kubernetes. Ceph and Gluster are out there. We tend to use a lot of NFS in our setups as well, and so we can just directly mount volumes, whether they are just connected over our local area network. And these pods can mount those volumes just like a file system. So it just looks like a file system to your application. It doesn't really matter what it looks like underneath. Now, that's all great because we've just saw that we have an application, it's wrapped into a container, that container is wrapped into a pod, that pod contains one or more of those containers, and then to wrap all of that up, we have another mechanism called namespaces. And what this does is provide that degree of isolation from other parts of the cluster. So if I have an application here in its own specific namespace, if I launch other applications in a different namespace, they don't talk to each other, right? There's no cross chatter. And again, this can help to isolate either application spaces. You can use it to isolate users as well on the system. So containers are cool and all, of course, and the reason that we use them is because it makes things easier. And we use Kubernetes to run those pods, those containers that we've created. But in machine learning, like I was showing you earlier, my notebook, there's a great tool that goes on top of Kubernetes, because really Kubernetes by itself is not that useful unless you're a skilled sysadmin, you're great on the command line, and you know exactly how to launch pods. And I'll show you how to do that in a minute. But let's be honest, most of our data scientists are not computer scientists, right? They're not writing command line. They're not doing, they're not in VI or Emacs. They're using Jupyter as their main interface to a system. So Kubeflow is a platform that sits on top of Kubernetes that they call it the machine learning toolkit, but I will say it's really a lot more than that. What it does is it really helps you to create these machine learning and deep learning workflows on Kubernetes, very simple, portable, scalable. So if I take Kubeflow today and I create a workflow for, say, pre-processing my data sets as they come in and retraining the model and then giving me results, once I have that running actually on my laptop or on my workstation, I can say, okay, cool, looks like I've got everything good. I'm just going to go check that into the main cluster and let the cluster handle that workload now. And there's a ton of components inside of Kubeflow. What I'm going to show you is the Jupyter notebooks, and we'll talk a little bit about using MPI inside of Kubernetes as well, which is also pretty important. So if you are not for the faint of heart, but you want to go ahead and do this yourself, you already have a Kubernetes system running and you just want to launch some Kubeflow, you can go grab the latest Kubeflow from Git, do some configuration scripts, generate them, install them, and then install a couple of different operators like the MPI operator, for instance, when I want to write parallel code to do training. Now that's complex. So we went ahead and we had continuously been standing up these systems over and over in our lab. And I just thought, man, we should really have a nice automated way to do that. So we created a software package here called Omnia. And I will just point you to the, it's on here somewhere. There we go. Right here on the GitHub, you can go and download this today. And what this will do is actually help you stand up a Kubernetes system. It'll deploy Kubeflow and get you right up to this point where we're working today. So again, Kubeflow, the easy way, just clone it. We run this playbook and then bam, we've got Kubeflow. Now, So let's say I'm a system administrator, and I'm looking to do some more, hands-on work. I'm also doing some research with my groups in TensorFlow, and they were looking at how do I do distributed TensorFlow, right? There's a couple of different ways to do it. You can use a parameter server, or you can use what's called Horovod package that the group that Uber helped develop. And what this does is allows us to do distributed TensorFlow training and using this MPI operator. So for all of our HPC people who are more than familiar with building code with MPI, this is a little different and interesting. So what we have here is this is the basic YAML that you would use to write your think of this as your submission script, like you would use in Slurm or PBS, et cetera. We have a lot of the same things that you would think about. This is just an app version that we're using, Kubeflow version 1. And the kind is important because this is going to be an MPI job. I didn't want to go that fast. And what we have here is you can just give it a basic name. Hey, I want to run the ResNet benchmark from TensorFlow. I want 2 replicas. And what that means is I actually want 2 full servers to be running this. Not just containers. Well, there will be 2 containers, but I'm going to force these 2 containers to exist on 2 different systems. And the way I do that is I reset some resource limits. So first here, here's the container that I'm going to look at. And in this case, I'm just grabbing that MPI operator example TensorFlow benchmark, just grabbing the latest one too. And I give it a name, and then I give it some resource limits. Like I have on this system, it's built up of C4140s, and they have 4 V100 GPUs per node. So the way that I can force this to exist on 2 separate nodes is say, give me the maximum amount of GPUs per node, and then make 2 replicas. So very similar to what we see in Slurm when you're trying to request lots of resources. And then here's just the command, which is just a classic MPI run of this Python script. That's my TensorFlow benchmark. We do declare some things like batch size up front because we know roughly what the memory size is for these images. And then the model that we declare that we want to use is ResNet 50. A couple of other things that we're going to pass to that Python script itself is the update variable, which is going to be Horovod. And Horovod, again, is a package that sits that works with TensorFlow so that we can do distributed work using the MPI framework. And what we wanted to show out of this was that we had a lot of discussion about over the last few years about containerized workloads versus bare metal workloads. And when we're talking about specifically about doing deep learning training, a lot of this work is happening on the GPU itself, and then there's a data exchange, and then GPU work, and then a data exchange. And we were looking at it saying, I don't really think you're going to see a huge, any sort of reduction in performance when you actually move away from one single system, or when you move away from doing it in bare metal. And so what we saw was that we did see a slight, in this test, slight performance loss because we were using IP over InfiniBand, but not really an effect on scaling, right? And that's what's important at first, because then we went and switched out our software-defined networks for Calico, and now we're actually seeing very, very close, within less than 5%, of the exact same performance, bare metal versus a container. I'm just going to check if there was a question. I saw it pop up, and it looks like people are answering. Okay, that's cool. There was a question about what does MPI mean on the one-liner. It's the message passing interface, and basically it's a library we've been using for far too long to help us build parallel code. So, is there anything else I had on containers? I'm at future techniques, so I think that is actually Luke now. I want to say one other thing about Kubeflow, though, just to kind of give you guys a little taste here before I let him jump in here, is I showed you this Omnia project, and what this does is really create a modern way to build a cluster. We provide an AWX interface that looks like this, so that the administrator can go ahead and look at, hey, I've got 5 hosts in the system. We can see right off the bat what they are, and then we can look at those inventories, and we can actually assign roles to all of that inventory as well. So let me see if I can find that here. Oops, hosts. There we go. So we can see them all in here, and then we can assign roles, and we can run playbooks on these. And those playbooks, like I said, help deploy Slurm, and they help deploy Kubernetes and Kubeflow. And so here you can see, here's my, I'm actually using a NGC container from NVIDIA to run that example that I kicked off today. And I have a few others that are running on the system that I've been playing with over the last 2 weeks. But basically, you can just create a new server. You can point it to some existing ones that Kubeflow provides for you directly from Google. You can create your own custom images, which we tend to do a lot. You can just throw them up in Docker Hub and then pull them in. And then really quickly, how much RAM, how much memory, or how much CPU, what kind of disk do I want? What kind of, how many GPUs and what kind? Right now it's just NVIDIA and up to 4. And you can do shared memory. You can do all sorts of cool things and then just launch that container. And once you do that, you'll see that you'll have these, this set of notebook servers that I was showing you, and you get to this nice Kubeflow interface, right? And now I'm actually getting very quickly up and running my whole data science platform. So that's where I wanted to leave you with thinking about how we're thinking about putting these systems together, why you're using containers, and why and why that's important. There's a question of I heard that Red Hat and NVIDIA are partnering to provide accelerated AI infrastructure. And is there an NVIDIA GPU operator for Red Hat OpenShift? Absolutely. There is an NVIDIA GPU operator for Kubernetes, and you can use that in OpenShift as well. And comment on Red Hat NVIDIA partnership and where technology combinations best suits or has best uptake. I don't really think it's anything specific to Red Hat. Let's be honest there. You can run SUSE, you can run Red Hat, you can run CentOS, you can run Ubuntu. As long as it's container native, that's really all that matters. We're very quickly getting to a point where we don't even really care what the operating system is. That's all preference now. As long as you can run a container, then we're happy. And the way that the vendors have started to look into it is, as long as you're running a container in Kubernetes, then we don't care either.
John, right. I realized I missed a question earlier up in here that Jeff had asked about the precision. I had some precision numbers across the bottom of one slide, and we probably I should have probably mentioned that, but I was going too fast. We are all used to people wanting to get from 32-bit to 64-bit, and the embracing 64-bit operating systems and 64-bit computations. And there's good reasons for both of those two. 64-bit operating systems can address a larger pool of memory. 64-bit computations have more bits devoted to both the mantissa and the exponent. I believe it's 11 bits for the exponent and 52 bits for the mantissa, so that you can do incredibly accurate computations and simulation codes. You all probably all remember that graphics processors, of course, did not used to be 64 bits and never needed to make that jump to 64 bits because the human eye can't resolve 64 bits worth of different colors. And so GPUs were stayed at 32 bits for a long time until people realized they could be used to accelerate physics computations. And then NVIDIA was the first to bring 64-bit computation to GPUs. Well, when the AI boom happened and people realized you could use NVIDIA GPUs to crunch these deep neural networks faster than with CPUs, you didn't need to use the 64-bit capability for the deep neural net computations, and especially not for the inferencing. Luke and John and I keep talking about the classifier that recognizes cat, dog, sandwich. That's just 3 objects. You don't need a whole lot of bits to recognize one of 3 objects, right? A couple of bits will do you there. So the inferencing systems, depending on what you're trying to inference, can be as few as 8 bits. And I've heard of examples of less. The training systems are often 32 bits and sometimes 16. In fact, a new format was created at 16 bits that is not IEEE 16-bit. It's called bfloat 16, and it's only 16 bits, but it has the same exponent number of bits as 32-bit numbers. So they sacrifice a bunch in the mantissa, realizing you don't need that great level of accuracy, but you can now benefit from 32-bit operations instead of, 16-bit operations instead of 32. So it's been really interesting that the simulation world pushed to larger and larger, 16, 32, 64-bit OSs and computations and whatnot. But the AI world has backed off that in favor of performance because it's a knob in terms of accuracy in the result versus performance. And typically, there's exceptions, and this is oversimplifying it, but typically you double the number of bits in the computation, you have the computation rate. So if having the accuracy helps you double the computation rate and doesn't really lose you anything because the accuracy was false accuracy above a certain level, you might as well use chips that are doing operations at a lower bit rate in order to get more operations per second. So you see a lot of AI processing done in training at 32 and 16 and at inferencing, sometimes even less than that. You've even seen Intel implement the DELL boost instructions in their Xeon processors, which I believe are 8-bit instructions just for inferencing. Is that right, Luke?
Right, they're 8-bit integers.
8-bit ins, yeah.
So it's a 512-bit vector of 8-bit integers.
I would say NVIDIA has done the best job overall of being able to embrace 64-bit computations on GPUs and then multiple precisions. They even have their tensor precision within their tensor cores in their GPUs now. So they have probably been the most aggressive and out in front in terms of embracing different levels of precision to provide the proper trade-off between enough accuracy and devoting everything else to performance. I don't know if that answered Jeff's question, but I hope so.
So let's talk about some future techniques, Luke. Show me what's happening in the state of the possible.
We only have 15 minutes left, so I'm going to very quickly go over just a couple of examples. And I just wanted to give everyone an opportunity to kind of marvel at some of the things you can do beyond identifying sandwiches in pictures. Although it is nearly lunchtime here in Texas, so identifying a sandwich sounds pretty good to me. But we have these types of systems that are actually combinations of multiple neural networks called generative adversarial networks. And these are interesting systems. So in these GANs, we have 2 different neural networks. You can see them in the boxes. There's a generator and a discriminator. And one neural network is charged with, the generator is charged with generating, in most cases, images in an attempt to trick the discriminator into thinking it's a real image. And the discriminator is tasked with trying to determine whether something is real or fake. And so we allow these 2 neural networks to train simultaneously using a combination of real world and generator-based images. And it does 2 things. It allows us to create better artificial images and at the same time create better systems for identifying whether or not an image is fake or real. And so you can do really interesting things with these. And so I'll ask everyone a question. Which of these pictures is of a real person? You can put it in chat or you can just think to yourself, but I want you to try and figure out which of these people you think is real. Let's see if anyone says anything in the chat here.
We got a couple of nuns.
Those are good guesses.
Those are great guesses.
Yep, none of these pictures is of a real person. All of these are synthetic. They may take traits from people you've seen before, but none of these people is real. And this is really the power of these generative networks, is they can start to produce very realistic images. And you can see they can even produce backgrounds. So they produce interesting backgrounds. They produce them either in, blurred or non-blurred. Sometimes they're gray. They produce shadows. So these images are produced in an effort to try and trick other neural networks into thinking they're real. And in the process of learning how to trick other neural networks, they learn how to trick us. And these types of systems that can generate very realistic images can be used for other interesting things. So this is a screenshot of a proof of concept that was built by NVIDIA for building realistic landscapes. So you can see that the artist drew the picture on the left. You can see that they're colored with different definitional things. So you can see you've got river and water, and you have sky, and then you have some cloud and some rocks. And what happened is once the artist filled in those very rough components, the neural network generated the image on the right in an attempt to do what the artist was hoping to accomplish. And you can see it's got grass and rocks and sky and clouds and a relatively realistic looking waterfall that it generated based on that very crude image on the left. So these are the types of techniques that can be enabled with these generative networks. And there's all sorts of other types of generative processes. So the artificial voice, that's a generative process. It's generating that audio during the inference step. It's not a stitching. So it's another example of a generative network. And this is where these neural network-based techniques are moving in the very near future. We're moving from a regime where we're only using it to make decisions, we're only using it to classify, into a regime where we're using it to create. And so there's lots of other examples. One of the great recent examples is DALL-E, which was connected to GPT-3 to allow the system to generate images of things based on kind of suggestions in text form. So if you're ever interested in just wasting a few minutes, get on the internet, search for DALL-E, DALL-E, and also search for avocado armchairs, and you'll find great examples of generated images of avocado armchairs and snail harps and all sorts of strange things that are built using these generative models. Another thing that is kind of on the horizon is reinforcement learning. And reinforcement learning is a form of neural architecture search. So this is a way in which we look for optimized configurations of neurons in a neural network based on some environmental reward system. So there are other techniques that are very similar to reinforcement learning. You have things like neuroevolution and algorithmic neural architecture search, which can build very complex neural network topologies that are sparse or dense and can do a wider array of things than what we're used to seeing in kind of traditional classification networks. And one of the interesting things that reinforcement learning is being used for is active real-time decision making. So in this case, if you think about autonomous vehicles, you've got several different types of neural networks being used at the same time. So you can see you've got object classification and detection networks that are running to identify the lanes, identify the cars, identify the street signs, and then using the output from those neural networks, you have networks that are generated by reinforcement learning in order to make the decision. Do I accelerate? Do I decelerate? Do I move the steering wheel to the left, to the right? Do I put on my turn signal? what is it I need to do at this exact moment, given the other information that I've received from the more standard classification neural networks. And so as we start to put these different forms of AI together into this multimodal regime where we have neural networks that feed into other neural networks, we can start to build very complex decision systems that start to approximate what would hopefully be considered an intelligent operation that's done by a human being. And with that, Jay, why don't you wrap it up for us? You're on mute.
So just a few final words. What have we covered today? Well, we talked about how machine learning allows businesses and researchers to identify relationships and model expectations. In most, if not all, fields of inquiry, people are finding new uses for this all the time. A key point here is that lots of data is required to train these models. So, as we think up that analytics stack, you only need 2 data points to fit a line, right? You can do that by hand and pencil and paper. But to train these deep learning models, you need a tremendous amount of data that you run these deep neural network computations on in order for it to find all of the features at all of the different scales that it's looking for in that data set, or that it can find in that data set, to have any hope of it being able to infer the existence of those features in any unique kind of way in new data. So in any high confidence kind of way with new data that it gets. So there's a general trend that the more advanced the technique, the more data it benefits from. And that's certainly true with deep learning. The more data, the good data, the better. Of course, we all know that the amount of bad, you must have good data to train these models or you can't get good results, but you also must have a lot of it. Deep learning can develop these models for mapping relationships in extremely complex and unstructured data. And it requires a little bit of a different way of thinking. We keep using things like the cat-dog sandwich, image classification as an example. But again, it doesn't actually know what a cat, a dog, or a sandwich is. It knows that if you provide it a bunch of images with those as labels, it will determine the commonalities in the patterns in the images with the same labels, so it can recognize those in new images. That's not the same thing as knowing what a sandwich or a dog or a cat is. And so you may think, well, that's not as powerful as the human brain. We understand the concept of what those things are, not just what they look like in 2D. But let me flip it around for you. There are plenty of things that we can't begin to hope to process the relationships between, and they may seem like unrelated things, but they're not. And I brought up the example of the DELL internal effort to do predictive maintenance on hard drives. And we can all understand that there could be a manufacturing flaw at a certain manufacturing plant that hurts a whole lot. Or maybe it's a time-dependent flaw at one plant that only hurts one lot. Maybe some of them are shipped in very rough ways to certain locations. Maybe some are used in different data center environments. You can imagine any of these things having an impact on reliability, but what a human's not very good at understanding is the weird ways multiple variables may come together to produce that. That is a difficult thing for us to calculate, but for all the lack of ability of concepts of these AI systems, they are immensely good at number crunching. They are cold, calculating, algorithmic number crunchers that are faster and more accurate than we are. So they really can become as good or better than humans in certain things. The AlphaGo was an example of that, where we thought for a long time maybe they'd never catch up to the best human experts, and now they have greatly surpassed the best human experts in that. They're very good at some image recognition. They've been able to use AI methods, and NVIDIA has a great podcast episode about they understand patterns, and patterns can be in time, and with enough scans of eyes, they were able to recognize a certain degenerative eye condition in early enough scans at a better accuracy than the people that were trained to read those scans and make a predictive assessment that ended up saving people's vision. So they have weaknesses and they have strengths. The strengths relate to finding these kinds of patterns that would be very difficult to humans to find, as well as being able to do many of them just faster. And John gave a great overview, which I really enjoyed hearing, on containers and orchestration and changing the way we develop and share software. I can't tell you how long I've been in supercomputing that we've worried about all these compatibility issues about moving from supercomputer to supercomputer and having to recompile it, or at least re-execute the makefile or something like that. And containers have just greatly simplified it, so much so that, you know, they're almost synonymous with cloud. They're not quite. The cloud native specifications say that you must have an abstraction of software from hardware. That abstraction we use is containers and VMs. And so it's essentially synonymous with it. It enables so much in our cloud computing efforts, but it enables this portability among developers in regular environments as well. And as Luke summarized, tomorrow's techniques push the boundaries even further. For as exciting as this all is right now, it really gets much more exciting every year. We're not in some, you know, there's been talk of AI winters, and will we see another AI winter? My feeling on that is no, and I'll share as my final thought why. We've seen AI winters in the past, but in the past we have had neither the total amount of good data nor the cheap enough compute power to really harvest all the benefits of things like deep learning. So it was academic summers or research summers, and then research winters caused by a lack of applicability of these wonderful techniques. They were great research, they made great papers, but they weren't really useful in day-to-day stuff. That is completely different now. When we unlock our iPhone, it is using a facial recognition technique. When we ask our Alexa device to give us our schedule for the day and the weather, it is using an AI technique. So it is embedded everywhere around us. I don't think there'll be any more AI winners. It is here to stay because we have the data, we have the compute power, and now we have enough examples of it. What will change is the things that Luke talked about, being able to go far beyond image classification and natural language processing into, you know, hopefully developing truly capable autonomous, not just autonomous vehicles, but autonomous systems overall, and having these things train themselves and become smarter and smarter and more capable. Applying it to robotics is going to be one of the big frontiers in the decade ahead, and so on. So we're super excited at the future. I mean, it's a great time to be in HPC and AI right now, but the next 10 years look is much more interesting.
Couple of quick questions. Let's see. Significance of unsupervised learning, maybe. Well, unsupervised learning is useful, but again, is only going to be as useful as the data that we can provide it. We've seen some good, Luke was pointing to the sort of growing in your own neural network in an unsupervised fashion. We see that work really well, but again, we have to go back to the end and have some provability and have some understanding of what that data may have in bias. So definitely another technique that we're really going to be looking towards.
The one thing I'll say is about unsupervised learning is it helps to solve one of the major problems we have with supervised learning, which is the data labeling problem. Labeling is if you look at the total time needed to, acquire data, label data, build a model, build a neural architecture, and then train a neural network. The data labeling is probably 80% of the effort. Mm-hmm. And so when we build these artificial intelligence models, it's really just human intelligence in the form of labeling that we've stuffed inside a computer. And so as we move towards better unsupervised techniques, it'll relieve a lot of that burden on the labeling step. Now, our current systems, our best current systems are all supervised. So the systems that provide us the best accuracy are all in the supervised regime. And the unsupervised space is growing, but it's still mostly academic. But I think it's going to grow significantly in the next 5 to 10 years.
Mm-hmm.
There are some examples that are appropriate sometimes of using two techniques. So using the classical machine learning method of clustering to try to identify clusters in the data and then use that to help you come up with stuff that didn't have a label before because you didn't know where the clusters were before. But now you have an intermediate step. It helps you identify your clusters. You come up with some labeling of the clusters that is relevant, and now you've got labeled data for the next step. So there are some techniques for at least trying to get some kind of labels on.
You end up with augmented supervised learning, where you have a handful of labels, and then you can use an unsupervised technique to help you generate more labels by clustering them together. And hopefully you have at least a couple of labels in every cluster, and then you can apply that label to everything else.
What I think is going to be interesting going forward is there's an awful lot of unlabeled data out there, as we know. And as Luke mentioned, a lot of effort goes into labeling that data. But knowing this and knowing the benefits of labeled data, at least some systems, I'm sure, will be changed in order to require or simplify labeling at the time of data creation in some way. And we already store metadata about our images that we take on our iPhone have a ton of metadata associated with them, but they don't label the objects that are in them. Facebook was doing something interesting for a while. People would put hashtags on the images they were posting, and the hashtags were often descriptive of what was in the image. That was sort of the point. And so they used natural language processing on the hashtags to start trying to label images that weren't previously labeled. I don't think their accuracy was very high because people get weird about hashtags and make up crazy stuff too. So, but I thought that was an interesting technique, trying to leverage what people were doing on their own.
One last question, the potential GPU shortage demand. Yeah, I mean, there's a lot of people that want it. There's a global chip supply problem, right? And it looks like, at least from what I can see, that some of the former US foundries or people who owned foundries are going to start kicking them back in mode. So if I had to take a guess, yeah, we're at a shortage today because of a lot of compounding factors. One is, if you're the business that has all the money and you're doing the AI, you probably have all the GPUs. Think somebody like OpenAI. But the other side is that cryptocurrency has become so popular in mining that a lot of those GPUs are being sucked up into that ecosystem as well. I think that within the next 3 to 4 years, though, we'll start to see maybe not a surplus, but definitely a steady stream of new ASICs and different, lots of different companies, not just GPUs, but other things as well.
And it's pretty cyclical. We saw a few years back when the cryptocurrency market sort of collapsed, that there was a glut of additional GPUs on the market, at least those in the lower precision space. And so it kind of wobbles back and forth. Now that demand is up again, there's a shortage, and then it'll go back to there being warehouses full of them that we don't know what to do with. But that's just the nature of the economics of it.
NVIDIA made an announcement recently that they are going to reduce the performance for certain crypto operations in some of their gaming GPUs because the gamers are upset that they can't get the 3000 series GPUs. And at the same time, they also said they're going to make a dedicated crypto processor. They had a nickname for it, and I can't remember what it was, but they are going to make a dedicated crypto processor as well.
I think we come to the conclusion of the presentations, Jay.
All right. Well, thank you guys very much.
Yeah, thanks for your time.
Yes, on behalf of Ulster University and ECME, thanks to John, Luke, and Jay for today's presentation, Sam for organising things here in Belfast, in Northern Ireland. And sometimes these afternoon sessions can be a little bit tricky because everybody's had their lunch, but fortunately we were blessed with beautiful sunshine today, so I think that's kept everyone on this side of the Atlantic alert. And of course, the excellent content, presentations, and examples and experiences you brought to the session is excellent. So again, thanks for getting early. Sorry for the technical problems at the start, but it's been a really worthwhile session for everybody. So thanks again.
You're welcome. And hopefully next year we can come out there and give it to you in person.
Yeah.
Yes, please do. Come at this time of year or summer or whatever. Because you can't guarantee the beautiful blue skies that we have today.
All right. Well, thanks everybody. Have a great rest of your week and weekend.
All right. Thanks, guys. All the best.
Cheers.
Thanks, everyone.
All the best. Take care.
Thanks. Bye. Bye.